Jnanam paramam dheyam. Knowledge is supreme.
Looking at how the x, y, z coordinates of each atom transform in response to every symmetry operation, we have been able to come up with a reducible representation, right. And if you remember, this is what the representation is. This is what we called gamma 3n 12 0 minus 2 4 minus 2 2. We will learn a shortcut to how to arrive at this reducible representation without having to explicitly look at the transformation of each of those xi, yi, zi coordinates one by one. Alright. So, if you remember, in the last class we took maybe 20 minutes to understand C3, what happens in C3, what is the character for C3, and then in 15 minutes we could work out all the other characters. Today we are going to learn a trick that will let us arrive at this gamma 3n without even having to do all that. Okay? And of course, once we know the trick, it is a black box. But the issue is that we should know how we arrived at the black box. That is what we are trying to do right now. Let us think a little bit how we arrived at gamma 3n. What did we work with? We worked with the x, y and z coordinates, right? And we said that any atom that moves from its position is not going to contribute to the overall character. Okay? So, essentially we have worked with the atoms that have not moved from their own position. Let us say the number of such atoms that remain unchanged by a particular symmetry operation is small n. Okay? Let us work out what small n is for every symmetry operation. How many atoms are there in the molecule? We are still working with BF3 or carbonate, 4 atom D3H. So, there are 4 atoms, right. How many of these remain unchanged upon operating E? E is the identity operation. How many atoms remain in their own place if I apply E? The answer is all, right, all 4. So, n is 4 for E. How many atoms do not move from their position upon applying C3 plus or C3 minus? 1. Only the central atom. What is n? 1. How many atoms remain in their place upon applying C2? 2, right. The way we drew C2 was through the central atom and one of the other pendant atoms. N is 2. What is n for sigma h? Does any atom move from its position? 4. What about S3? I have got 2 answers, 4 and 1. Which one is correct? Or is there any other answer? 1? Sure. Only the central atom remains in its place. All other atoms change place, like C3. What about sigma V? 2, right? The 2 atoms that are in the plane, like C2. So, this is n. Now, what I have to do to arrive at these characters of gamma 3n is that I have to multiply each n by the character of the representation that we get by using x, y, z as basis. Is that right? After all, if you remember, it does not matter whether it is x1, y1, z1 or x2, y2, z2, x3, y3, z3, x4, y4, z4. They transform in the same way. The blocks are all the same. It is just that the atoms that move from their positions, for them the non-zero blocks go off diagonal. That is why they do not contribute. Do we agree that blocks were all the same? Remember C3? Aren't the blocks all the same? Right? Minus half, root 3 by 2, root 3 by 2 minus half, 1. Everything else is 0. This is what you get for each of the blocks, because after all x, y, z transforms in the same way no matter with which atom it is associated with. Depending on whether the atom moves from its own position or not, you get that block along the diagonal or off diagonal. Are we clear about that? Right? So, how did we get a character of 0 for C3? How did we get a character of 0 for C3? We multiplied the character of this block by 1. Number of atoms that did not move from its position was 1. We multiplied that by the character of this. How did we get C2? Once again, same blocks, only the diagonal blocks matter. 2 atoms don't move from their position. So, character multiplied by that atom. Okay? So, that is basically what we have to do for everything. N we have worked out already. Now, to do it, we need to know how x, y, z transform with upon operation of each of these operations that are there, upon using each of these operations. So, tell me how will I get the character of what I call gamma x, y, z. Gamma x, y, z is the reducible representation for which x, y and z form the basis. How do I get gamma x, y, z? Remember what we did for water? For water, we used x, y, z as basis, and then we got these matrices for this basis, and then we could nicely block factorize them, right? That gave us the 3 reducible representation. So, for water C2V, it turned out that gamma x, y, z is equal to A1 plus, does anybody remember what it would be for x, or what it would be for y? We can work out quickly actually. Will it be A, will it be B? If I take x or if I take y, will the character of C2 be +1 or -1? Water is very easy, we can work it out anytime. X, y, z, right? This z is the C2 axis. Will the character of x and or y be +1 or -1? -1. So, will it be A or B? B. So, A1 plus B1 plus B2. Which one will be B1? Which one will be B2? How do I decide 1 or 2? Character of Zx, sigma V if you remember, right? So, which one will have a character of 1 for sigma V Zx, x or y? X is on the plane, so character should be 1, y is perpendicular to the plane, character should be -1. So, A1 is for x, z, B1 is for x, B2 is for y. Okay. So, gamma x, y, z can be written as a sum of irreducible representations where A and B belong. For this D3H, what am I doing? What is gamma x, y, z? Sum of which? So, now we are doing the reverse process. Here I had given you gamma x, y, z, and then we broke it down into constituent irreducible representations. Now, I have shown you the character table. You already know where x belongs, where y belongs, where z belongs. So, what is gamma x, y, z? How do I get it? Just by adding them. Where does x belong? Where does y belong? Where does z belong? X and y jointly form the basis for E dash. E dash is, don't forget, is a 2-dimensional representation, and z is in A2 double dash, right? It is not just A2. So, for D3H, gamma x, y, z is E dash plus A2 double dash. Are we clear about this? If there is a question, please ask. Did you understand what I did? Can I go ahead? Okay. So, if this is the case, gamma xyz is E dash plus A2 double dash, then I should be able to find the characters of gamma xyz by adding the corresponding characters of E dash and A2 double dash. Is that right? Can you tell me what the characters will be? What is the character for E? I can tell you that it's going to be 3. What is the character for gamma xyz for C3? Yes. What is the character for E dash? -1. What is it for A2 double dash? +1. What is the sum? 0. Understand? We are just adding characters. So what will be the character for C2 dash? Yeah? C2 dash? 0 plus 0 minus 1? Is that -1? What will the next character be? What is the character for sigma h? Yes, 2 minus 1 equal to 1. What is the character for S3? Yeah, -2. This is just addition. So, all right. What is the character for sigma V? Now he is bored. 1. Okay. So this is gamma xyz. How should I be able to get gamma n, gamma 3n now? If I multiply n by gamma xyz, should that not give me gamma 3n? Let us see if it does. It does, right? I mean, you should work it out. 3 4s are 12. 0 into 1 is 0. -1 into 2 is -2. 1 into 4 is 4. -2 into 1 is -2. 1 into 2 is 2. So what we have established is n multiplied by gamma xyz gives me 3n, gamma 3n. So to work out gamma 3n is the reducible representation for which the 3n coordinates of motion form the basis, can be worked out by simply looking at the character table, working out the reducible representation for which x, y, z are the basis, and multiplying it by the number of atoms that do not move from their position as a result of each symmetry operation. Alright. So now that's the shortcut. Okay. But it's not the complete shortcut. We are only halfway through the shortcut. So what we have established is this gamma 3n is really n into gamma xyz. Now, what am I trying to do? Am I really interested in the 3n coordinates? We are trying to arrive at the symmetry of normal coordinates of vibration. All these are normal coordinates, but we are only interested in normal coordinates of vibration. This is the symmetry of all the 3n coordinates. I am looking for symmetry of 3n minus 6 coordinates. How do I do that -6 from here? What are the 6 coordinates that I have to deduct from here? X, Y, Z for translational motion, movement of the center of mass, and Rx, Ry, Rz, right? So this is your gamma xyz, you have worked out already. What is gamma rot? Gamma rot means the reducible representation using Rx, Ry, Rz as the basis. Can you work that out for me? Rx, Ry, where do they belong? E double dash and A2 dash. So if I add E double dash with A2 dash, then I should get gamma rot. Can you work that out for me? Let's work out gamma rot by adding the irreducible representations for which Rx, Ry, Rz are the basis. Answer? What are the characters for gamma rot? 3, 3 0 minus 1, minus 1, 3 0 minus 1, minus 1, hold on. Rx, Ry, Rz. So here I made a mistake. 0 minus 1, then minus 1, 2, minus 1. 30 minus 1, minus 1, 2 plus 1, right? Then we can work out gamma vib from there. How do I work out gamma vib? Yes, simple. So gamma vib is equal to n multiplied by gamma xyz minus gamma xyz minus gamma rot. In fact, when you want to use this formula as a black box, it makes sense to do it directly and write n minus 1 multiplied by gamma xyz multiplied minus gamma rot. What will it be? What is gamma wave? Tell me. Yeah? N into gamma xyz is given, gamma xyz is also given. So 12 minus 6 should be, first of all 6. Oh, I actually did not work it out. That is why I have such strange numbers. So I have 6. Then what is it? What do I have next? What is this character? Second one? 0. Third one? No, that is wrong because that is just gamma rot copied. So don't think what you see on the projection is right. I did not finish making the transparency today. Yeah, it is 0. Then what do you have? 4 minus 1 is 3, right? Minus 1 is again 4. Is that right? Is that 4? See, I am not very good at mental arithmetic, so you need to tell me when I go wrong. Then minus 2, isn't it? And the last one? Two minus 1 is 1. 1 minus 1. Is this the answer we all get? Gamma wave is 600, 4 minus 2, 2. Is that right? Is that right? What is the next step? Did we derive a small working formula in the last class which tells you how to break down a reducible representation into its constituent irreducible representations? What was that? So we said that we write a reducible representation as sum over I, ai, gamma I, okay, and the way we find ai is, or aj, way we find aj is, what was it? 1 by h sum over r chi j r x, not x, chi of r, where chi of r is the character of symmetry operation r in the reducible representation. Chi j of r is the character of r in the jth irreducible representation. Okay, this is our working formula. Using this working formula, can you work out the values of a for these symmetry operations that are there, sorry, these symmetry species that are there in this gamma wave, which is a reducible representation? Can we do that? Is the problem defined? Have you understood the problem? No. Are you okay with this? So I am asking you to find aj for a1 dash, a2 dash, e dash, a1 double dash, etc. for this gamma wave, which is a reducible representation. See, gamma wave is a representation. What is the dimensionality? 6, because character for E is 6. Look at the character table. Is there any 6-dimensional representation? No. That means this is a reducible representation. So I should be able to write it as a sum of irreducible representations, right? So I want you to find out the coefficients of each of the irreducible representation that is there. Okay. So, your job is essentially to multiply 6 by 1 plus 0 by 1 plus 0 by 1, 0 multiplied by 1, 4 multiplied by 1, minus 2 multiplied by 1, plus 2 multiplied by 1, divide everything by 12. How much time does that take? I have the answer. I have the answer for the first coefficient. It is very easy. What? What is the answer for the first one? For A1 dash, what is the coefficient? 1. Is that right? 1. For A1 dash, there is, the coefficient is 1. That means there is one totally symmetric vibration. And in fact, when we showed you the normal modes without deriving, we had shown you this symmetric stretch, right? That is the totally symmetric vibration. Alright, what is the coefficient for A2 dash? Half? It won't be half. Anything other than half? See, this always, that is a check. The coefficient will never be anything other than a positive whole number, positive integer. Half cannot be, you cannot have half a vibration. Okay, let us work it out. 1 multiplied by 6 is 6, plus 0 plus 4 multiplied by 1 is 10. Is that right? Plus minus 2 multiplied by 1 multiplied by 2. That is where we always go wrong. Do not forget, you are summing over all R, and there are 12 symmetry operations. The way you get 12 symmetry operations is by counting S3 twice, right? So, the reason why you got half is because you forgot the coefficient of S3 and sigma v for that matter. Are we getting 0? Are we getting 0 or are we getting 1? Zero. So, coefficient of A2 dash comes out to be 0, right? There is no A2 dash vibration. What about E dash? E dash is even more interesting because E dash is 2 dimensional. What is the coefficient of E dash? 2. So, let us see what we have so far. We have gamma vib is equal to A1 dash plus you are saying 2E dash, right? Can you tell me how many normal modes are accounted for so far in what I have written? How many normal modes have I accounted for? 1 A1 dash and 2 E dash. So, how many is that? So, this is the second point where we often go wrong. It is not 1 plus 2, 3, but 1 plus 2 into 2, 5. Do not forget, E dash is a 2-dimensional irreducible representation. So, each E dash contains 2 vibrations that transform together. Okay? Look at the character table. What does E dash contain? X, Y. What does that mean? That means X and Y are not separable. They transform together. But X is one coordinate, Y is one coordinate, right? So, it has 2 coordinates. Similarly, whatever normal mode of vibration you have, there are 2 in each E dash. We have accounted for not 3, but 5. What I am trying to say is this. Do not, first thing is what we have said already, do not forget to multiply by the coefficient because we are talking about symmetry operations, not symmetry elements. Second thing very important to understand is do not forget that when you have a more than 1 dimensional representation, their dimensionality gives you the number of elements in the basis. Okay. So, when you have E dash, that is a 2-dimensional representation. Each E dash stands for 2 coordinates. That is what you see in the character table. See X, Y together, that is 2 coordinates, isn't it? X, Y together is not 1 coordinate. X is 1 coordinate, Y is 1 coordinate. Similarly, X square minus Y square is 1, x phi is another. Together they transform, that is why it is a two-dimensional representation. So, each E dash actually contains two coordinates of vibration. So, one A1 dash and 2 into 2, 4 E dash vibrations. Have you understood now? So, we have only one left to do. If you account for one more, we are done. Alright, what is the coefficient of A1 dash, A1 double dash, sorry? That is the job of whom? 0. No A1 double dash vibration. What about A2 double dash? A2 double dash? 1? Sure? So, if this is correct, then of course, the last question is only a formality. What is the coefficient of E double dash? 0, right? We have accounted for all the normal modes already. There are 6 normal modes, we have accounted for them. So, what we say is, there is one totally symmetric representation, one A2 double dash vibration, and there are 4 vibrations that belong to E dash. Okay? So, this is where we have got so far. Next thing we want to know is, can we now say a little bit about what kind of molecular vibration, which bond stretch, which bend has what kind of symmetry. Okay? That is what we will take in the next part of the discussion.